Okay, I think I'm ready to start recording this now after getting all this installed. So what I'm doing today is working on this Carleson project. So for a bit of context, this is Carleson. This is a project from Flores to state this theorem, I guess an important theorem about Fourier series. And it has this this blueprint. You can see, like, for example, the dependency graph, right? This is like the graph of all of the statements here that are part of like proving this theorem. And so you can work on it. And I've requested to prove one of these lemmas, which seems relatively simple to me, just to like try and get started. So I think I'm going to try and proceed with that. So the lemma that I'm looking to prove today is this geometric series estimate for all real numbers x greater than or equal to 4. Sum from n equals 0 to infinity of 2 to the minus n over x is less than or equal to 2 to the x. Okay, and so that is what we want to proceed with. Now, let's proceed with the proof. So everything seems above board here. This is the trunk. This is the like the t sum. This is the like version of sum which you can define on any sequence, and if it like diverges, it defaults to 0. So sum n equals r 2 to the minus n over x. So my sort of first question is like, should I immediately simplify this to, right? If I have 2 to the minus n over x, that is the same as, let me make sure I'm getting this right, 2 to the minus 1 over x quantity to the power n. Yeah, that makes sense. And so that's, something, a sequence of things raised to the power n. Right. Raised to like successively greater powers of n. That's like I don't know, is that like version of the zeta function or something? It's not something that you can do like the it's not something where you can do, or wait, no, I'm getting this wrong. Zeta function is when the like the base changes. Yeah, okay. So 2 to the minus 1 over x, all raised to the power n for larger and larger powers of n summed. And so really it's just a geometrically decreasing series. And, there's the standard formula where, like, I guess it's this part of the formula, right? Sum n equals 0 to infinity of 2 to the minus n over x is equal to 1 over 2 minus this thing. 1 over 1 minus this. And so what is the point of all this other reasoning here? Let me just look. By convexity, something is true, right? The point is that we need this inequality, right? In order to prove this is less than or equal to 2 to the x. We have this is straightforward. So I guess the thing to do here is to go to the docs page and try I would think it would be something like geom sum. I think I've seen that. Geom sum. Thin set range. But I want t sub. This is a t sum. Geom t sum, perhaps? T sum geom. T sum pow. Okay. Maybe the semantic search will help. Google. Sum of an infinite geometric series. ENN real. T sum geometric. Is this it? T sum geometric. Something raised to the power n equals 1 minus r. Yeah, inverse of 1 minus r. This looks right. Cool. Now it's specifically for extended non-negative reals, which is not what we just have real numbers here, right? But presumably t sum. Okay. So okay, what am I trying to do here? My first goal is like div, right? I want to extract the minus n here because I just want it to be n. So it's probably okay. The first thing I have to do is get the n out of this expression. Pow div. Is this sum? So we simply do this. That all fine. What's the problem? Failed to synthesize h pow n r. No, okay, I'm wrong. These aren't non-negative reals. They aren't extended non-negative reals. They're non-negative reals. variables. They're not extended though, because there's no infinity. Doesn't this only like hold for like appropriately small r? I guess that's what the non-negativeness is about, right? R, I mean, if r is greater than 1, this obviously diverges. RHS equals infinity. Okay. So I'm beginning to suspect that there's some like things slightly missing here. Like I might have to. Okay, let me like copy this and go back to the regular docs. T-sum geometric and n real. R less than 1. Yes. Well, I think we have that, right? Because r in this case is -1 over x, and we have x is greater than 4, so -1 over x is a negative number. So this is all well and good. Yeah. Okay, but we're still okay. We're returning to the problem that's showing on our screen. We're failing to synthesize. What is the issue? The issue is that I just need to copy exactly what was written down. And the point is that this is -1 over x. Sorry, okay, is it n? Okay. Let me just put it in the like final form. Right, that whole thing raised to the power of n. Let me. Yes, so now I'm trying to prove this. And now I just apply congruence. Conger, oh, and I can like supply a number. So conger 1, what does conger 1 do? Do I have something slightly different here? Oh, I have n. How did that happen? N-R. What? Is this just a typo in the lemma statement? Because it's saying we're summing over n, a real number, which is obviously a really strange choice of variable name, and also, yeah, like, what does that even mean, to sum over the, like, all real numbers a certain quantity? That's just a, as I recall from, it's like sort of an ill-defined concept to even consider that. So I think what's going on here, let me also like return to the theorem that I thought I needed. Sorry. We're summing over natural numbers here. Okay, I'm pretty confident that this is this should be a sum over natural numbers. Luckily, everything still works out. I'm gonna declare it to be natural numbers here as well. Okay, what happens if I do like unbridled conger here? Yes, so x to n, simp. And now I want to do like pow or something. These give me anything? Not really. So this is r power, and this is rnr. What could be the name of that lemma? Mul. Problem is that it's like rpow. Mul. Yes, but these are when they're both rpow. Rpow mul. Real rpow mul. Yes. But the remaining question is, what about when z is a natural number? It seems like a good candidate for library search, perhaps. Theorem. Y is a real number, and I'm going to say that n is a natural. The theorem that I'm looking to prove is that times n equals x to the z to the n by exact. Imports are out of date and should be rebuilt. You're not, okay. It's beginning to insist. Has already been declared. Rpow mul nat. Rpow mul nat cast. Is that what I'm doing here? Yes, I'm casting to something. Okay. So we found it. So I think I'm gonna try and apply this backwards. So we write backwards this. Did not find instance of the pattern in target expression. This is a real. This is a real. This is a natural. A to the power b. What happens if I... Am I insane? Okay. I don't understand. This works, but the lemma itself does not. Oh, is the problem that I need like the namespacing? Yeah, okay, cool. Because clearly our PowMol netcast, like without the real namespace, will be some other weird thing. Okay. Let's play Conquer again. Field, North. Okay, no goals, cool. Simp is a text point. Yeah, okay. Simp question mark. Well, that is fine. Yes, very good. Okay, so we've done that. Now we rewrite this. Well, this can be like converted to calc block later. And now we want to apply the like geometric sum lemma. T sum geometric NN real is what we wanted, I believe. Because we have, this is when R, right, the base here is an NN real, right? It's R, it's NN real. So, and is there like a namespace on it? I'm confused. I think namespaces always show some things. I mean, this is sort of like someone should change this from being named tsum geometric NN real to being named NN real dot tsum geometric, because that feels like the proper thing. It's also interesting that this is a simp lemma, but this is not. I guess the point is that maybe it's. I guess the point is that there's this parameter here. Okay, rewrite. All right, so this spalls off a goal of the form. Now this is interesting. I haven't seen this. Like, it's slightly smaller. The unfocused goal is slightly smaller. Right. Okay, and now we have to like prove some fact. We have to prove this. We have to prove this. The point, yeah. So we can do we can do this first. Have by failed to synthesize. Sorry, we need to constantly be putting in this type description, I think. And the reason that this follows is because 2 to the power of something is less than 1 when that something is positive. So yeah, exactly when the thing is less than positive. So it should be something like apply pow lt1 failed to unify pow lt1 underscore 0 failed to unify. Okay, but it still failed to unify. Failed to unify a to the power n less than 1 with this. Okay, the point is that this was requested to be something like that. This is a non-negative real. What does it need? Pow lt1 needs, no, this is not what I'm trying to apply here, right? Pow lt1, the power a to the power n is less than or equal to 1. Pow lt1. Seems like we have a bunch. Yeah, we're trying to say that a, well, no, we're trying to say that a is greater than 1. Pow lt1. I saw an if. Pow lt1 if. Well, linear order, x to the power n is less than or equal to, is less than 1 if and only if x is less than 1. No. Is this some sort of, is this only for some like very specific kind of type? That's annoying. Yeah, clearly if x is like 1/2 to the power 2, that is less than 1. And but if n were negative, for example, oh, n is in natural. But yeah, this is not what I want. There's just a whole ton of things. Okay, I don't want something where the thing I'm raising the power to is in natural. What I want is a thing where the thing I'm raising to a power 2 is like an arbitrary type. Well, what is it? It's a real, right? Real PAL LT. Let's try real PAL LT1. Real PAL LT1. RPAL perhaps. PAL LT1 if. Okay, but the problem is that this is actually a non-negative real. 2. Can I like simplify away the like type being different from real? Right. I want something is less than 1, where 1 is greater than or equal to x, and z is less than or equal to 0. Is this what I want? It seems like approximately what I want. We have that the base is greater than 1, yes, and that the thing is negative, which it is. So, I'm sorry, my cursor is not tracking. This one is basically the one that we want to apply. But we're going to run into the fact that, oh no, we didn't run into it. Wonderful. It obviously like figured out the type thing itself. Okay. Simp. And does the positivity, solving goals of the form like this. I'm surprised that this doesn't simplify to, sorry, -1. Now I can simplify that away. Cool. Great. And of course I'm violating the good practice here of always doing this. Okay, that's great. I think did I violate this multi-goal linter? Yeah. Arpel mul netcast, like bilinerith. Great. Cool. So now we have so let me just start naming things. This is 2 PAL negative LT. Now I want to do this t-sum with this hypothesis. Okay, now it's complaining about simp being such a tactic. Okay, that's cool. Okay, so cool. Now I can like deal with that without generating 2 goals at the same time. And now we like proceed. Okay, so let's return now to the guide, right? So all of this was just to get us from here to here, right? And now we have to show that 1 minus 2 to the power of -1 over x, all the inverse of that, is less than or equal to 1 over 4, 1 minus 2, this. And that is less than or equal to 2 to the x. By convexity for all 0 less than or equal to lambda less than or equal to 1. Right. So what we're being advised to do here is, okay, let me just look at this. Lambda to the 1/4, 2 to the -1/4. Okay, so okay, what are we doing here? We are using the convexity of the function 2 to the x on the interval from 0, on the interval from -1/4 to 0, right? Yes. So we have like 2 to the x from -1/4 to 0. And for any in that range, for any lambda in that range, lambda being the coefficient of -1/4, we can say that the linear combination of those two things is greater than this value. And so sure, let's proceed. Let's proceed with this. By convexity, we have that, yeah, so like convexity. We actually like have some kind of like convexity. Convex PAL. Convex on PAL. In fact, it would be nice to just like say convex. Was there something that I missed? Convex POW? Convex on. Convex on, convex on, convex on. Okay. Let me try and delete this. What is this? X to the n. What is x here? X is a linear order common ring, so presumably the real numbers works. Or even is convex x raised to the power n. But we're not doing raised to the power n here. It's convex on here. What I want is that, what I want is not like this to be an integer. What I want is that the function where the base is fixed. So this is not right. Convex POW. Convex on POW. Yes, the function. No, this is wrong as well. Shouldn't it be like convex on rpow left or something? Rpow left, right? Okay, there was this other one. This is also one where it's a... It seems to me that we should have, in fact, a theorem about the fact that 2 to the power x is a convex function. Or, you know, replace 2 with whatever base you want. That's not some weird exceptions, but it's on POW. It doesn't work. That's not what we want. Okay, annoying. I can type it in the other way. I mean, I assume that whatever name it would have convex in the name, and it would also have POW in the name. But I'm not seeing anything like that, right? So POW convex doesn't really turn up anything, right? Sorry, POW convex. None of these are right. So convex and POW. Strict convex on? Convex if pointwise. No, that's not right. This is when it's an even number. Strict convex on z-pow, strict convex on r-pow. I mean, it should have a different name. Let me see if I can like do this search engine. 2 to the x, sorry, 2 to the power x is convex. Nope. K to the power x. This is x to the power n. That's not what I have. Okay, as a last ditch effort, let me try the other search engine, which I think is called Lean Search. It seems so implausible to me that it doesn't exist. X to the power p. Yeah, no, I want to say the function of x where x is the convex on exp, right? So this at least is right. Convexity of the exponential function. This is always the base here. Yeah, I'm not seeing it. I'm not seeing it. Like, how hard would it be to prove? Presumably it would not be too hard to like prove the statement from this. Is this like a, go to doc. I feel like that's like an AI generated thing. Yeah. Collection of convex functions. Be in here. One would think it would be like next to this. X to the P, but none of those are convex. None of those are what we want. Okay, I'm beginning to think that this is like not present at all, because I feel like it would be in this file, right? Like for any like b other than 0, b to the x is convex function on the whole real line. Okay, I just want to like put this in the is there code for x, because it's just like I'm just very surprised. So what was the name of the exp convex function? Was it exp convex? Something was convex on x. Convex on x. Yeah, no, this is not the version. I need the version where it's in the exponent. Convex POW. Do we have a lemma? tells us that fun x e to the x is convex on the whole real line. I expected to find this, but couldn't. It holds for any like non-zero b. Doesn't it hold for 0b? When b is 0, I forget exactly how it's defined. Okay, so that's just a little slight mystery. What I'm going to do instead is, because I think this theorem will exist. So I'm going to just replicate that theorem. Theorem, how left, convex on, strict. Left, and the function that I won't claim it is convex on is the function fun. Yeah, no, that is wrong. B to the x. B is not defined because I haven't defined it. B is a real number. B is not equal to 0. HB 0. Fail to synthesize. So x is why is x being a natural number here? Fail to show termination. I don't. Okay, the AIS generates here. Sorry, but I believe this is a well-formed statement, right? Yeah, HPL RRR. Okay, so I think that this is what I'm looking for. Here, just kind of like double check that no one has spoken up. Okay, so we can, yeah. So let us assume this theorem as a very easy theorem. This is just true, right? So yeah. And assuming this is a theorem, let us return to the like proof guide here. Yes. By convexity, have strict convex, yes, by norm num. In this case, we don't necessarily want to, just want this to be that, and by arith, let's say. So we have, yeah, 2 pow convex. Given that we have 2 pow is convex for all 0 less than lambda less than or equal to 1. We should just have both of them. Let's not screw around with that. Let's just have the convex. That's simpler. So by convexity, what do we have? By convexity, for all lambda 0 less than or equal to lambda less than or equal to 1, we have is there some way that I can like open up the context? Right. This is, I mean, this is why Kevin always says you like, it's good to have the LaTeX inline because that way it will like auto formalize for you. Okay. So we simply this, right? And And now I will like specialize. So convexon has some kind of definition. Let's take a look. Convexon, what is the definition of convexon? Convexon, it means, yes, for all x and for all y, for all a, b, right, it's defined in like a super convoluted way, but yes, so this is f, and a and b are respectively lambda and 1 minus lambda. Yes, so a here have who is 2-pow convex. Okay, so let's try and do all of our variables here. So what am I applying it to? I'm applying it to the x and y. I'm applying it to are -1/4 and 0. So x, right, so let me just, I don't know, like this is like one of those weird sort of -1/4, the real number. Let's just do x. Just like make sure that this is clear. Sorry, it's a real number. And it's enclosed like this. 2-pow convex. Convex on. Sorry, what is, okay, we have a convex on, but we also have convex. That's like incredibly confusing. Convexity of sets. Yeah, so we need to do some weird arg cases stuff here. Arg cases with like, I don't care about that. Arg cases, how's that supposed to go? Yeah, I'm supposed to do something like this. Convex. Okay, so that gives me this. Yeah, 2-pow convex with x is equal to this. We can basically like x is equal to this. The fact that it is a member of the set is by simp. Y is equal to 0. By simp. We don't have any z. That's dumb. The next argument is a. We have to yeah, a and b. So the point is that we're doing it for like 1/4 or something. Just a sec. No, the value of lambda is what we wanted. So for lambda equals 4 over x. A equals 4 over x. By Lenareth, by, I just need a bunch of arguments here, sorry. X equals 0, y equals 0, a equals this, by, and like this is where we're proving that this is true. Oh, sorry, that out for now. B equals 1 minus a. Sorry. 1 equals 1 minus a. 1 minus 4 over x, whatever. The fact that b is greater than 0 is another object of debate. We then, okay, what is next? Sorry, I'm gonna delete this other stuff, sorry. Delete this, yeah, okay. We have to prove, yeah, no, this is wrong. We declare a and b, and then we separately do the fact that they're like well in the right range. And then we also have by sorry again to prove that they sum to 1. And then the result is simpet foo. I'm just gonna call this h. Let's see if we can like read the result. What h? 2 to the, okay, so like, is this what we were supposed to get? 2 to the power of minus 1 over x is less than or equal to, yeah, so lambda equals 4 over x, right? So 4 over x times 2 to the power -1/4 plus 1 minus 4 over x, 2 to the 0, which is, of course, 1. Okay, so that looks right. So I'm feeling good about that. Cool. And the thing that we're supposed to obtain, it wants us to like rewrite it slightly. Okay, so I'll have to rewrite that slightly. I'm going to take a quick break and come back. Okay, right. 2, so I mean, already it's looking about right. So 2 to the power of minus 1 over x is less than or equal to 4 over x times this plus 1 minus 4 over x. Yeah, and so it basically just wants us to shift this around a little bit. It's like 1, yeah, we have 4 over x here, and we have 4 over x here, and we have a 1 minus something here. So it's 1 minus all of that. Right. So to like return, what is going on here? I think that, yeah, I think the point, okay, so like how do we get from this to this inequality? I think the point is that this 1 minus 1 over 2 to the minus 1 over quarter. Yeah. 1 minus this, right? So I think the point is that we flip this, right? So if 1 minus this equals that, then 1 minus that, sorry. If this is less than or equal to 1 minus that, then it's also the case that that is less than or equal to 1 minus this. And so if we have 1 minus this here, we can say that, so this quantity is less, right, than 1 minus that. So if we are decreasing the denominator, right, we are making things bigger, right? So thus we get this, and from that we get less than or equal to 2 to the power x. This is like a really weak, strangely weak bound. Like, so you're telling us we prove that it's actually like less than linear? Why is it necessary to, what is this explicitly? This is 2 to the minus 1 quarter, right? So like this is the 4th root of 2. It's like something, you know, something like small. But the point is that this is all probably less than like 10x. I guess we need it for small x is the point. Okay, right, like I'm starting to get worried about like this final thing here. The point is that 1 minus, okay, let's try and work out exactly what this is using our trusty calculator. 1 minus 2 to the power of negative 1 over 4. So this is like 0.15. If I multiply by 4, this is 0.636. And if I do 1 divided by all of this, okay, so it's just it's slightly more than, it's like halfway, about, you know, 1.57 or whatever. And we're saying that 1.57x is less than or equal to 2 to the power x, which is a fact, that itself requires proof, which is perhaps non-trivial. Very easy to prove by graphing calculator, not necessarily easy to prove to lean. Yeah, so that gets to be the part of the library where you start to need to like take logarithms. Yeah, how do you what's like the best, most straightforward way of proving that kx is less than or equal to 2 to the x for k for which that's true? This is where it would be nice to have like a tactic that like evaluated such things for you. Yes, proof by graphing calculator. I guess the point, x is greater than or equal to 4. Right. So the point is that we can say something like, okay, for x greater than or equal to 4, 2 to the power x is like just some very large number. It's like 16 times. We probably have like a trivial bound of the form like x is less than 2 to the power x, and then we can apply that to like 2 to the x minus 4 or something. Okay, so I feel confident we can get there. Right. Well, x is positive, so positivity. This is another thing. Simp. Field simp. What the heck? FIELD. It's doing the ligature. Why is it doing that? Is it because I opened it in this like container? Field simp made no progress. So we simp. We do right tively. What am I supposed to do? Does it work? It does work. \__0. Cool. And of course that spins off more goals. But the point is that this is a linearith. And this other one is positivity. Oh, okay, I understand. This is like the non-terminal simplinter is like got very complicated functionality now where it like alerts you of all the like various things. Okay, cool. And then this is by ring. Cool. Okay, so we have our formula. We have our key formula, which we're calling H. So now we have this. What were we trying to get to? Yeah, right. So we agreed that the operation that was being done was we have this is less than or equal to 1 minus this. And that was the same. Okay, so we need to do some more manipulation here. I'm just going to, I feel like it's actually ending up being more appropriate to put it here. So that's fine. So H is this. I just want to say have this is equal to 1 minus 4/x times 2 to the whatever. 1 minus this. Sorry. Fail to synthesize. Okay, so these are not natural numbers, of course. This is x. This is r. I fail to realize that everything is a real number here. Yeah, and the thing, right, of course, the thing, sorry, let's just make sure that in here, in h, they are 1 minus x. Yeah, this is a real number here. Okay, so this is a real number. Cool. Real numbers all around. Real number by. Oh, it's non-terminal simplinter. I would just like to disable it while I'm doing the proof. I need to like look at the instructions for how to do that. Presumably they're printed out somewhere, but it's not like I know where that is. Okay, so this is true by ring. We write this at H. Clear this. Okay, so now we have that in that form. Can linear combination prove inequalities? I think it maybe can't. But the next thing we want to do is now change this so that it's 1 minus this. Okay, so copy this. Have H2. We want to subtract this. We want to have this on this side. And it's still the case that we're dealing with reals by linearith. Cool. So we have H2 now, which is that formula. And now we want to show that that is less than that. So the next order of business is have H3, I guess we'll say, is that this is less than or equal to, let's like try and put it in this form, right? We have 4/x. So yeah, let's just copy and paste this. Sorry. This is approximately what we want. And the okay, so like apply inv. It's going to tell me to use the _0 version, _0. I need to be a rewrite lemma. Point is that it has spalled off some goals. I don't quite get it. What is the, if 0 is less than A and 0 is less than B, is there a version which is a bit less like requiring me to prove so many things? So it's presumably this lemma. No, that's maybe not what I want. Okay, fine. I'll just prove this. I'll just prove all the things here. Write this. This falls off a whole bunch of different lemmas. Sorry. So the reason why that is true is exact. Sorry, this isn't exact. Sorry. Select the line. Next, sorry. Do we have justification for this? Justification is that we're raising 2 to a positive power, to a negative, like 1 over x is positive, therefore negative 1 over x is negative. Therefore 2 is raised to the negative number, so it's less than 1. Did we get this before? This is just we have this here too. Linearith, perhaps. Copy. Paste. Let's like prove this whole thing for to a real number. And now does the linearith work? Yeah. And we proved that this is greater than the other one, right? So the thing that confuses me is, shouldn't this be linearith? Because we have 4 over x times this here. 1. The point is that 2, we just proved by linearith that this is positive. And now the point is that, oh, so sorry, this is for proving something negative. Maybe, okay. Okay, no. The point is that this is by like positivity. Failed to prove. Okay, I'm not crazy here. This is positive because x is positive, and this is positive because norm num says so. So apply mul pos. Am I insane? Apply real.mul pos. What did I just type? Mul pos. And that looks like what I want. It's just this, right? Am I crazy? Ambiguous. Fully qualified name. Root. This is the one I want. I want the root one, please. Yeah. Now positivity. And norm num. Norm num? Does that work? Unsolved goals. Norm num. Oh, it's not a calculator. Oof. Okay. I mean, this is like, this shouldn't be too hard to prove, right? Let's leave it sorted for now. And we can also insert this. Okay, so now we have H3 in our context, which is this. So I think we're doing apply LA trans here. H3. And something else that we don't know yet. Apply a tactic failed. Failed to unify. Convert. Convert, perhaps? Yes. Oh, no, it doesn't work. Sorry, never mind. But the issue, what is the issue? The issue is that we have R, in one case, is a real, and in the other case is a non-negative real. Sorry, it's the 1 that's the issue? Okay, that's a little annoying. 1 is real here, but in my goal, it's a positive. Okay, this is not the sort of H sub that I want. Where did this come from? I think this comes from up here, right? Yeah, that's not right. Oh, it comes from the lemma? Go to definition. Ooh, that's annoying if it's true. Yeah, one is that kind of thing. Okay. Yeah, just to think about this a little bit. Is this true for all reals? Because yeah, we need r is less than 1 so that this can r is less than 1 ensures that 1 minus r is positive. Otherwise it would be being negative, and that's not good. So I mean the key insight here is that this would be true even if we were to cast things to reals and do real valued subtraction in here, and then potentially cast back to and then reals, which should itself be a lemma. Real sub, yeah. It should just be a lemma. This whole lemma should just be about real numbers. Whatever. T-sum geometric. Did I not conclude that like T-sum geometric right in this range? Can I do this lemma instead? Let me just see. T-sum geometric. Because it's in the right range, right? T-sum geometric of LT1. Yeah, I mean, this is the right lemma in principle. Yeah, the point is I want to get away from this. So can I just say that 2 is a real number here, in fact? Can I like push cast or something? So now I'm doing this. What happens if I try push cast? No extensionality theorem found. T sum r, T sum r. Now I try conquer. Xn. Now I like synth more, please. Conger, ring, no goals. Did not find instance of the pattern in the target expression. Okay, the problem is that I cast it or something. Because now this is something about a cast. I would just rather this whole lemma not be about non-negative reals. I would rather it be about just reals. Is there surely there's a way of doing that, because I believe that like the LE, like it would be preserved under a cast, right? Right. If x is less than y is less than or equal to y as real numbers, then there are less than or equal to each other as non-negative reals, because you probably like cast or something. Let's see if I can prove that. What I am claiming is that it suffices to show suffices foo. It suffices to show the case where 2 is not this by virtue. So here 2 is a real, here 2 is this. But like convert this. Convert this. Oh, this is some real. This is a real. I think this is something I can do. Okay, now we've got some weird expression here. Okay, so some like weird problem arises. Okay, this is all annoying. This is all very annoying. Rewrite veiled. Yeah, can I just undo? Can I just undo all of this to the point where it was working before? Yes. So most of this was working before. And the point that I got to was here. And I determined that I had h sub in here, and I don't have, sorry, I have h. H3 was about reals. Can I make this about, alternatively about real 0? doesn't seem to work. Would I be able to like simplify at this point? Can I simplify immediately? No. So the question is there some function like nreal dot lereal? Yeah, some like coercion function. So the point is that we have some nreal. We are casting it to a real. We want to show that it's less than some other real. So an real that we're casting to a real. This should be the same as, it should be simpler than this. It should be like a simp lemma of some kind. Simp. Sorry, what, does simp do something here? An real co-inv. What does it do? Co-inverse. Coercion of the inverse is the inverse of the coercion. That's sort of not the direction I want to go in, right? I want to not simplify with that. Okay, time to break out the like additional lemmas again. Theorem. If nreal dot coe real. So we have x is that. I'm also going to say that y is simply a real. Sorry, which way am I trying to go again? I want to show that it's equivalent at, no, this is actually like, sorry, itself. We have two different underlying types. This is right. The problem is that one of these things is fundamentally like a real number, and one of them is fundamentally a non-negative real number. What does the simp do? Maybe the simp is what I want to do. Why does im not work now? We have some real that we're taking the inverse of. We have some real that we're taking the inverse of over here. Except there's a times x over 4. What is this? Okay, the point is that we want to get rid of this other stuff. Simp. Only with this. Now we do that. And now the point is that we have the h sub over here, and we have the cast to real of the h sub over here. So this is like, but here we have a real, and here we have a real. So let's try apply trans this maybe. That's alt goals. Right. Simp only t sub if right. What? Truncated substitution. Yeah, it's a truncated subtraction. Is less than c if and only if that is the case. There's no other simps to do. Right, the point is that it's not trivial here, because what we have here is a truncated subtraction. And what we have here is a non-truncated subtraction. Yeah, the trouble is that this is like some weird tricky thing. Right. When you're doing naturals, you just like cast to the integers, but I can't do that here. Is there like an RFI tactic? RFI. Not tactic. Too much. Such an inelegant proof anyway. Should definitely like be a better proof. Yeah, I mean, really what should be happening is that the whole thing should be proof for like maybe like here's the like kicker, right? What should be really done is like this entire proof should be copied out like lemma. I'm just gonna call this like real version of the geometric series estimate, where 2 is a real number and everything is a real number. Reals numbers. And okay, so the lemma that we wanted, that we were back over here somewhere. Did I delete it? Or maybe I was like in the file, right? Go to definition. T-sum geometric and unreal. Oh, yes, very good. But the point is that I'm using the real version of this lemma, which is T-sum geometric of LT1. And that's perfectly fine. And like these other two things follow. One of them follows from by assumption. Assumption. And the other one should probably also follow by assumption. But it doesn't because we have not shown that yet. Okay, like, and clearly we can remove all the like the weird crap here. Yeah, I mean, it shouldn't be too difficult. It should be like relatively analogous, right? Because like we just have the real version and the non-real version. Yeah. So this is what we have. This is that we have that this is less than 1, and we also have to have that it's greater than 0. So this is LT1. Copy it out. Should have that 0 LE this. We can name it 0. This feels like it can be a simple application of positivity. And so now we have the two assumptions. Yes, great. Yeah, I probably could have just written positivity here, frankly, but whatever. And now we have this. We're keeping everything real. Everything is fine up into here, and we're going to, again, keep everything real. This was an exact, yeah. I guess what I should do before I like go too far down this road of doing everything with the reals, I should try and make sure that I'm like not going insane here. I think my point is that I have these two, right, LE over R, yeah, so these are non-negative reals. But in order to prove this, it suffices to prove that that if I cast them both to reals, it works. And then there's a question, okay, well, is the like T-sum operation amenable to casting over reals? Let's try and prove this. So I need a like an unreal cast suffices. I'm going to do the weird thing where I just cast to the thing that I think it is, non-negative. Sorry, this cast to the thing I think it is, cast to the reals, cast to the thing I think it is, which is R, G, 0, T-sum koi. Am I crazy? What just happened? Right, so I did transform the goal here, right? Previously this, and now, okay, I did exact, and it worked. Okay, so this all apparently worked. Great. I would suffice simp or push cast. Great, there's no sorries anymore in this. Cool. So I was, yeah, I'm golden. I didn't need any like fancy thing because it's push cast is smart enough to push it through the T-sum. Cool. And so now I can deal with the like purely real version. Great. So where was I? I was here. Yeah, so this is like just a fact, a like brute fact about numbers that would be possible to prove somehow. I can apply LE trans and this. Okay, so where am I? So like ignoring this one, sorry, which is like some numerical fact. Okay, I'm about to get yelled at by the linter. Actually, let's let the linter yell at me and see what happens when the linter yells at me, because I want to know how to disable the linter for now. Okay, so where did we get to? We got to something times x over 4 is less than 2 to the x. Yeah, okay, this is about what we were supposed to have. Yes, great. And I had done that calculator math earlier, and I determined that this quantity, or the quantity, okay, so we've moved the x outside. That wasn't exactly what we wanted to do here. Okay. Okay, apparently the simp linter is not going to yell at me. What happens if I do simp here? Ugh, so hard to get the simp linter to yell properly. I thought it was supposed to yell in such cases. Simp. GEFLE. Is this some weird? Okay, I don't know what the deal is there. We've applied this. Yes. So we have this, and okay. The next order of business is to show that this is equal to, x. We can bring the x out. So let's do that. H4. This is equivalent to this, but multiplied by x outside, and no dividing by x in there. Sorry. Again, we are doing reals. Here we are in the proper place. Does field simp work? Cool. Yeah. Write H4. And now we so yeah, this is the point where we search the library for like totally random lemmas of the form something less than 2 pal. Let's like go to Looble, for example. Looble. Something less than 2 pal something. So it's greater than 0. True. Does it support? Okay, so in this case it's a real. 2 as a real number, right? Apparently not. 1 LT 2 pow. The concerning thing is that all of these are for like real numbers, whereas I am mostly interested in something. Okay, so I can add something that says like real. Yeah, that's unfortunate. Okay, can I even find the equivalent thing for like natural numbers, for example? Like I know there's like a classic like demonstrate some proof where it's like prove that x is less than or equal to the x as natural numbers, and you prove it by induction, even though it's like a really like loose bound. Right. Like what would be a good way proceeding to prove this? Like this lemma. Take a look at this lemma. N is less than 2 to the power n. It's just a random lemma, but this may be like the break-in, you know? So we have a natural number. So, right, so like to think through, right, this number we've decided is approximately 1.5. So 1.5 times x. Right. I think the line of argument we want to take is something like such and such is less than or equal to something which is less than or equal to 2 to the power of floor x, which is less than 2 to the power x. And so, right, so like proof plan. We have 1.6 times x is less than something, which is less than 2 to the power of L floor. Sorry, wait. Floor x, which is less than 2 to the x. And the point is that the lemma that I'm going to apply here is, okay, so this is not going to work, but it almost works, right? The point is that we do this, right? And the only issue is that 1.6 times x is not this. But, like, okay, so the thing that we actually want to do is like a bit of jiggery pokery with x minus 4 plus 4. I think what we want to do is we want to say something like, because x is at least 4, right? X is at least 4. So if I'm talking about this, this would be equal to x minus 4 plus 4. X minus floor 4 plus 4. So I'm just doing it like so. Yes, now I've added and subtracted this, right? And okay, I mean this is getting to be ridiculous. Before I do this, I want to use the fact that, okay, so I have this. This is equivalent to this all times 16, say. Right? Cut like times 2 to the 4th. 2 to the 4th. Which is simply 16. And I can also, but because x minus 4 floor, right, that would, like, x minus 4 is greater than 0, and so the floor of it is a natural number. And so I can go further, and I can use this lemma here and say that this is like that. And then, like, the remainder will be solved by Lindroth. Right, maybe like throw in for the juice a little step here, which is like 2 times x, just to like get it back into the right. And like, okay, another thing is that I have this floor operator here. The floor operator is less than the ceiling operator of x minus 1, right? So this is, or really just, I could say like x minus 5 here. And because x is sufficiently large, maybe not. Because, okay, maybe I should have gone back and changed all the 4s to like 3s or something. Change all the 4s to flip to 3s. This, all the 16s become 8s. Right, so x minus 4 is less than the floor of x minus 3. Less than or equal to the floor of x minus 3. We have x minus 4. X is at least 4. Do I need to do 2? That's getting dicey. Two, all the 8s become 4s. X minus 3. And the point is that x is at least 4. So this is at least 1. And so this reduces to 3. Right, so the critical thing is this one, which reduces to 12 is less than 2x, which is not something that holds. Ugh. Yeah. So frustrating. There should be like something much simpler, right? Log 2. Isn't there, I wonder if I can take the, like, so if I duplicate log 2, yeah, real log 2 near 10, right? So like they have these like approximations of log 2. And so I wonder, like, okay, so maybe there's like an alternative approach. We're trying to prove 1.6x is less than 2 to the power x. The other approach is to take the natural logarithm of both sides. So that gives us x times log 2 on the one side, right? Okay, so alternative, like 1.6x is less than 2 to the power x. I can take the log 2 of both sides, and it becomes x times log 2. And this becomes log of 1.6. Okay, like just for fun, let's try and make this a 2 here, so that this becomes log 2 plus log x. And now we desire, log 2 plus log x. I wonder if like there's any reasoning about like the point at which that log lt log 2 ltk, yeah, maybe le would give me something. Real dot log x, real dot log y, harmonic lore, sum of consecutive reciprocals. Doesn't feel right. Right, how do we prove this? Right, okay, maybe the key is you have to first, yeah, so this is what you have to like manipulate the x first or something. Okay, so this follows from this, right? Copying this line out, this is equal to 2 times 2 to the power x minus 1. Simplifying, we are proving this. It's always so surprising how hard these stupid lemmas are to prove. Like in theory, it could all be done by some tactic. 2 less than x less than 2 to the power x minus 1, right? Right. So we want the weak bound. What is the largest constant for which this holds for all positive x? I guess it's 2. Shouldn't there be some lemma of the form like log x is less than something? Log x is less than 1 minus x. Self sub 1. I'm not crazy that like e to the x's. Real log, yeah, okay, here we go. So yeah, backing up yet again. We get into this state. We haven't used yet that x is greater than 4. Log 2 plus log x, and now we use log x is less than or equal to x minus 1. So it suffices to show x minus 1. Okay, I have a sneaking suspicion this is going to go wrong somehow. Right, because this one is growing too fast. Right, the problem is that it's not like a pure question of, it's like log x over x minus 1 bounded above. Log div x sub 1. Yeah. Log div self. Right. This reminds me of like the Bertrand's postulate proof that I was working on all those years ago, whereas like you have to like go through this nightmare to prove like obvious facts. Right, the fundamental reason why I think this should be true. Like what? I mean, the funny thing is, right, x, like the fact that x is greater than 4. Like, can I just like, this is annoying. let me like switch to y. Let y equals x minus 4. So y is the positive thing. So what we need is 2 of x minus 4 is less than 2 to the power x minus 4. We're not leaving the reals yet, so we can, okay, so it's minus 16, so it's 2 to the x now. This is still positive, right? Right, so we have this. 32 times x minus 4 is less than 2 to the power x. The fact that we need to prove for all positive y, sorry. Okay, I did this wrong. Frustrating with myself. Okay. Y equals x minus 4. Therefore, x is equal to y plus 4. Yes, the AI is smarter than me. Thank you. Okay, I don't want to do that. I'm just going to copy out this line. And I have a 16 over here. 16 times this. I mean, like, how close is it to not being true? Let me like think through this. If I think about x equals 4 itself, right? We have 4, we have like 2, we have 16 on the right-hand side, and we have, you know, like 10 on the left-hand side. It's not even that, like, it's not even that particularly obvious that it's not even that, like, far away. Yes. Of course it's always like the one inequality that's not explained is the hardest. It's just sort of funny. All right, 1.6. Let me like see if I can recall things that were done with the Bertrand's postulate to like massage all of this. There was some. Let me see if I can like just pull that up. Math Math library. Type to search. Bertrand postulate. This one. Real-main inequality. See, we like prove this sort of nightmarish inequality here. But the thing about Bertrand's inequality was you could actually like push the bound, because you basically just have to prove that it's true for sufficiently large n, and then you can like check all the cases below. Whereas here we have the problem. Let me get my like graphing calculator out actually. I just want to like see if I'm my like intuitive. So if I have y equals like 2x, let's say, and a new equation where y is equal to 2 to the power x. Right, that is actually like false. It is not actually true that 2 to the x is always less than, but it is true for x greater than 4. And it's also true for x greater than about 3, right? Like if I wanted to say that this is true for x greater than 3, I mean, the way of doing that would be to say that like z equals x plus 3, or sorry, x minus 3 equals z. So z plus 3 equals x. So I would have 2 to the 3 plus z. Yeah. It would be nice to just have like a bunch of linear bounds on the exponential function. Because what happens if I return over here, if I return to like the logarithm plan, let me just like quickly reconstruct it. What it is, we have log 1.6 equals is less than or equal to x log 2. Plus log x. Which amounts to saying that x, log of x is less than or equal to like this quantity. So it's less than some like linear bound. So like a number of linear upper bounds on the logarithm. I mean, it's true. Sorry, to return to the grapher. Right, the point. Yes. The point that I'm demonstrating here is that it's is it somehow like I go here And replace this by like 1.6. Does it like just barely kiss? No. Yeah, so presumably what needs to happen is there needs to be some like bound, some like, you know, work through like, so I think like technically it holds for all x, right? That is greater than the logarithm for all like positive x. Right, because the point about the logarithm is that you can just like shift and rescale. So the point is that we shift and rescale until we are proving a theorem of the form log x equals -1 times something times x. -1, yeah, logarithm of x. Let me write that again. So we're proving that log of x is less than this. Now clearly we already have log of x is less than -1 plus x, or x minus 1, another way of saying it. But the issue is that x, yeah, technically, I just have to remember that technically this is true for all x. But the problem is now I'm getting into the business of approximating this 1.6 value. Let me just like, what is the 1.6 value? It's this thing, right? This thing. 1/4, 1 minus 2 to the negative, right, 2 to the negative 1/4. Well, I'm sure I can find a rational number to approximate this, right? Because what I do is I just find a rational number that approximates this expression sufficiently closely, and then I do, you know, like a rational bash to get it into a form where I have 2 to the power of -1/4 is bounded by some rational number. And then to prove that, what do I do to prove that? How can I get an expression of the form like a rational number bounds this? How can I prove such a bound? Or such an approximation? I guess I use the log base 2 stuff, right? I say like, okay, this is approximately this, you know, this is in between these two rationals. Right. If I take the logarithm of this, right, yeah, so 2 to the power of something. Yeah, let me just think this through. If I have 2 to the power of something, 2 to the power of a rational is hard. 2 to the power of something is equal to the logarithm of 2. I want p over q is approximately equal to 2 to the power of something. So log pq is going to be equal to, it's going to approximate -1/4 log 2, which I can approximate because I have log 2. But then the question is, how do I get back? Because I have log something. Log p over q is approximately equal to some rational. So going back, we have e to some rational, e to some specific rational. What a fracas. Racus, however you pronounce that word. It's true for all x, in fact. Right. The point is I have to shift it to the point where it's 0, and so then I have an expression. Well, I guess the point is I already have an expression of that form, right? 2 to the power x, right? So like, you know, in natural form, right? Natural form. What happens is I say like this is equal 2 to the power x is actually e to the power of x log 2, which is equal to e to like the power of x to the power log 2. Let me just like continue rewriting here. The point is I can do like the shift thing, which in this framework would equate, yeah, so we've done this. Log 1.6 plus log x minus log x. I don't know if I'm making any sense. The point is that we have to shift it, I guess, to the point where it intercepts at -1 rather than 0. Because the point is that when we take the logarithm, what we're saying is that the logarithm of x is less than x log 2, right? It's plus this, right? I don't know why there's an extra thing here, right? We take the logarithm of both sides, we get this. We subtract off the log 1x, and so we have log x is less than this linearly bounded thing. Now, the point is that, okay, so this is the natural log, this is some like slightly negative thing, and this is some slope. The thing is, I think we want to be talking about log of x minus 1, right? We want to be talking about log of x minus 1 so that the other term is what we want, because we can just as easily say that log of x minus 1 is less than or equal to x. So this is what we're trying to prove. We're trying to prove this. We're trying to prove this for all x. So we're trying to prove this for all x. So it suffices to show this. X minus 1. It suffices to show that. Or in other words, this expression. And so now we have log 2, right? So this is a slope. Log 2 is less than 1, right? Minus log 2. Point is that minus log 2 plus log this can be alternatively written as log like 0.8 or something, because we divide by 2, which gets into the negative territory. Wait, I'm confusing myself here. The point is that we have to shift it. We have to shift it. What we're supposed to be able to, what we're supposed to do is we're supposed to do like the appropriate shift so that we get it so that we're proving that something of the form like x plus k is greater than log of x minus 1. Shouldn't we be able to do that somehow? I guess the point is that no, because because like the slope and the intercept are like moving together somehow. Maybe the logarithm plan take 2. Maybe this is what we're supposed to do. We're supposed to prove this for all x, right? And so the first step is supposed to be something like the first step is to like divide, so replace x with x divided by 1.6. This yields x over 1.6. Now we take the log of both sides. Yeah, okay. This is what we're supposed to do. Right. We can just substitute in y equals x over 1.6. Yeah. All right. Well, that was. Okay. I'm still not sure this is right, but x times log 2 over 1.6. We still have to like approximate this stupid 1.6 thing. But the point is that no, this is also not right or something, because this is going to be less than 1, and the question is how much less than 1 is it? At this point we do another substitution. The point is that we now have x, right? So it's just a multiplicative factor here. So now we do like yet another substitution. Log of x minus 1 x minus 1. What I really want is like x, like just the expression x minus 1 on one side, because I want to see what the logarithm looks like. So this is logarithm plan 2. Maybe I can like understand it better if I do it a third time. Logarithm plan 3. What I simply want, okay, all right, so like trying again. This is log x over log 2 plus log 0.6 over log 2. Okay, I'm gonna have to like put some more thought into how to do this, but for now I'm gonna sign off.